Dear friends, this lecture is to expose you to the theory of pressure drop in ducts and fittings of the ducts. I mean, we would be revising some concepts, especially the concepts from fluid mechanics, and seeing that how these concepts are vital in practical life. I mean, in the design of duct systems and selection of fan in the HVAC system. So we would begin with the concept of what is known as the fan total power. Fan total power is related to the fan total pressure. So I have represented in this W fan as the input of electricity, input of power or rating of fan, which would be necessary to overcome the losses in the duct systems. So when I'm saying duct systems, I'm including not only the ducts but also the duct fittings. So in order to estimate this power consumption of the fan, we need to calculate what is known as the fan total pressure. And this fan total pressure, we had done a video on this fan total pressure. So this fan total pressure would include many things, but the most important thing is we should be in a position to calculate the pressure loss in the ducts and the fittings. Okay, so the basic concept when you talk about determination of pressure loss would come from the very fundamental equation which we have studied in fluid mechanics. So that equation is known as the Bernoulli's equation for ducts. This Bernoulli's equation for ducts can be written as, if you are writing it across section 1 and section 2, it would be P1 plus half rho V1 square plus rho GH1 is equal to, this is at section 1, P2 plus half rho V2 square plus rho GH2, where H1 and H2 are elevations. Commonly, if it's a horizontal duct, these elevations would be the same. So this would cancel off. And if there is no friction loss, this would be the equation of Bernoulli's. However, what we see in practical life is that there is a pressure loss. And this is the pressure loss which we are interested in computing. Okay. So the entire objective of today's lecture is to concentrate our attention on this pressure loss. So the pressure drop in the ducts, why do we find that there are pressure losses in the ducts? We need to understand that these are because of two things. One is because of the friction. The fluid friction would result in the pressure drop in the ducts, and the second thing is there is a momentum change, and this momentum change would result in what is known as the dynamic losses. So the dynamic losses are because of change in direction of the flow of the air in the duct. It could be also because of the magnitude as well as directional change. It means that velocity change. Okay. So this pressure drop in the duct systems, when I'm saying duct systems, I'm including everything, including the duct fittings, are attributed to these two factors, that is the fluid friction as well as the momentum change due to change of direction and or velocity. Okay, so the latter is known as the dynamic losses. Now, in order to calculate the friction, we know the very popular equation which is used in fluid mechanics, which is known as the Darcy-Weisbach equation. So this equation helps us to calculate what is known as the frictional pressure drop in the ducts. This is a commonly used equation, you know, and this equation I have written over here is delta P equals to FD, where delta P is the pressure drop, FD is the frictional factor, which is called as the Darcy frictional factor, into L by D ratio, which is where L is the length of the duct, in our case length of the duct, and D is known as the hydraulic diameter of the duct, into rho V square by 2, where rho is the density of the fluid. In this case we are talking about air ducts, so air density would be considered, and V is the velocity in meters per second. In this case we are talking about the air velocity. Okay. So this equation, which is a popular equation in fluid mechanics, helps us estimate the pressure drop in the ducts because of friction. This friction factor is function of Reynolds number, and it's function of relative roughness of the duct. Okay, and there is an equation by Coolbrook which helps us to calculate this friction factor. Okay, so this is the basic fundamental equation which helps us to calculate and arrive at what is known as the friction chart. So the friction chart, this friction chart which I have shown over here, is a friction chart which helps us to calculate the pressure drop because of friction in straight circular sheet metal ducts at 20 degrees centigrade, and when the absolute roughness is 0.00015, okay, meters. So this sort of friction charts one can use, okay, where you find that on the y-axis there is a flow rate. In this case it is given in meter cube per second, and the pressure loss is given in pascals per meter. Okay, so this kind of friction charts one can use, and we have done a separate video on the friction chart for calculating what is known as the pressure drop in the straight ducts. Okay, so this friction chart would help us calculate the pressure drop in the circular ducts, but if the ducts are rectangular, then also this friction charts can be used by first calculating what is known as the equivalent diameter. So equivalent diameter can be calculated by knowing the dimensions of the rectangular duct, where A and B are the dimensions of the rectangular duct. Okay, the cross section A and B, right? So using A and B, one can calculate the equivalent diameter. So using this aspect ratio, the width and the height of the rectangular duct can be calculated, and we can use the flow rates, and then we can use the friction rate to calculate this pressure drop. Okay, so even if the ducts are rectangular, we can use the friction charts for the circular duct by making use of this concept of equivalent diameter. So this is explained in a detail in the video on friction chart. Okay, so you are referred to that video for understanding this concept better. Now, the second important thing is the fittings. So air handling system consists of straight duct as well as the fittings. Now what happens in the fittings is that the air undergoes, as was mentioned earlier, the changes in the area and the changes in the direction. So these fittings would include many things like sudden enlargement, which is shown over here. It might include contractions, as would be shown in the next slide. It might include the elbows, the branches, the dampers, the filters, and the air registers. So the air pressure drop in these fittings must be known in order to design a system properly. So in the actual system design, the pressure drop in these fittings may be of more concern than that in the straight duct. Okay, So that is because you'll find that in this fittings there is much more pressure loss. Okay, and how do we estimate this? So there are two methods. One is either to calculate the equivalent length. For example, pressure drop in an elbow may be equivalent to 3 meters to 12 meters of straight duct, and it could also be as high as 20 meters. So pressure drop in an elbow has to be determined by calculating the equivalent length. To understand the importance, see that if you are talking about an elbow, it is equivalent to about 10 meters of straight length duct losses. Okay, so it is very, very important to arrive at the pressure drop in the ducts. So the pressure drop could be because of the sudden enlargement, as I said. It could be because of sudden contraction or even gradual contraction. It could be in the elbows, it could be in the branches, and other equipments like dampers, filters, and registers. So how do we calculate that? Okay, so we need to keep in mind that when you use the ASHRAE handbook or any data book for arriving at this, you would find that the coefficient any data book would give you the pressure law drop by calculating what is known as the loss coefficient into a term which is rho v square, or in some books it is written as C or V, whatever you use, stands for velocity. So this is the typical way of expressing the pressure drop. So in fittings, you'll find that this pressure drop is always expressed as the loss coefficient into this term. Now, what is this term? This term is called as the velocity head. Okay, the grouping of this is very important, where rho is the density, C or V is called as a velocity, and you would find that this into the C naught, where C naught is because of the geometry of this duct, would give you the pressure drop. So you'll always find the expressions. For example, in sudden enlargement, this expression for pressure loss is like this. You get the pressure loss expression when there is a sudden enlargement like this from section 1 to section 2. It would be delta P loss is equal to this expression rho V1 square by 2, which is a velocity head, into 1 minus A1 upon A2 bracket square. This is in pascals. Okay, so it's very interesting. So it is a function of this cross section area A1, and this is a function of this cross section area A2, and we can prove this equation by applying what is known as the Bernoulli's equation. So by writing the Bernoulli's equation for section 1 and 2, you can determine the pressure loss because of sudden enlargement. Okay, and in the ASHRAE handbook, if you know this A1 and if you know this A2, you can straightway determine this loss coefficient. Okay, so it becomes very handy if you are using a data book for calculating delta P loss because of sudden enlargement. Okay, so we can use two methods. One is by using the basic equation, that is Bernoulli's equation, for calculating the pressure loss, or the second one is, as I said, you can refer to the data book. Okay, this equation which I used, okay, is known as, there's a special name to it. It is known as this is just for academic interest. Okay, it is known as the Borda-Carnot equation. Borda-Carnot equation, and you will find this equation in fluid mechanics textbooks. Okay, so just remember that we can use this equation for calculating pressure drop in the fittings. Okay, like when there is a sudden enlargement. What if there is sudden contraction? If there is sudden contraction, now where do you there is sudden contraction means what? A sudden contraction occurs in the duct section where the duct size is abruptly reduced in the direction of flow, like this. In the direction of flow, there is an abrupt reduction. It could also be a gradual reduction. Okay, so the flow pattern in a sudden contraction is as shown here. You see that there is a separation of the fluid from the wall. Look at this. There is a separation of the fluid from the wall, and as a result of this, as a result of which there is a vena contracta formed, and this vena contracta which is formed, you can skip this if you are not interested in much of the fluid mechanics. You can skip this, but this is called as what is known as a vena contracta. And using again, applying again the Bernoulli's equation, you can calculate the pressure drop because of the sudden contraction. So I'll be writing that equation over here. So delta P loss because of the sudden contraction is again expressed in the form of the velocity head into the geometry parameter. Okay. Into 1 minus, this is, suppose this is your A1 dash. If I call this as A1 dash, so A1 dash upon A2 upon A2. Okay. Or if you know the area of the vena contracta, you can also obtain an expression in terms of what is known as the contraction coefficient. Okay, contraction coefficient. So if you know the contraction coefficient, C naught is equal to contraction coefficient and you can get the expression in form of the delta P loss. Okay, so in your actual data book, you don't require to use all this equation. You just have to refer to such kind of beautiful tables to arrive at the pressure drop in the fittings. Okay, so this equation you can remember, the equation which is derived from the Bernoulli's equation, which helps us to calculate the pressure drop in the fittings because of sudden contraction. If there is a converging transition like this, converging transition, not this is a sudden contraction and this is a converging transition, in that case you are referred to this sort of tables. Okay, you would find that in books this contraction coefficient values are also available. So this is one of the important laws because of sudden contraction. Then turns, bends, elbows. Okay, these would contribute in a major way to the pressure drop in the duct systems. So the most common elbows which are used in the duct systems are 90-degree elbows. This is 90-degree elbows. The 90-degree turns, either circular or rectangular in cross section. Okay, it could be a circular in cross section or rectangular in cross section. And Hvac, he proposed that the pressure loss in an elbow is due to the sudden expansion from the contracted region. Okay, so because of this change in direction by 90 degrees, there is a sudden expansion from the contracted region, and as a result of that, there is a pressure loss. Okay, so the pressure losses can be determined for the circular cross section as well as for the rectangular cross section. If it's the rectangular cross section, then this aspect ratio and this W by H, which is which describes the geometry of the rectangular cross section, decides the pressure drop. So it has been found that this W by H ratio has to be kept low, and this can be kept low by using what are known as the turning vents. So I shown here the turning vents. Okay, you can do Google search on what is a turning vent. The only thing to be understood is that if we use the turning vent, if you are using turning vents like this, these are the turning vents. If you are using the turning vents in this cross section, then this would decrease the W by H ratio and this would reduce the pressure drop. So as compared to an elbow or a bend without the turning vents, the pressure drop would be less if you are using the turning vents. Okay, so use of turning vents is desirable, right? The next area where we need to look for the pressure drop is known as the branch takeoff. Now, what are these branch takeoff? So let me just try to show it over here. What is known as the branch takeoff? When there is a main duct, okay, this is the main duct. Let us say this is the main duct. I'm drawing a broader picture, and if it has to supply the air to different rooms, so there has to be some branches. Okay, so there is a branch over here. From the main duct, if you want to supply it to a different area, so this would be a branch. Okay, this is what is drawn is a branch. Okay, so let us say that this branch is at an angle of beta. This is angle of beta. Let us say this upstream velocity is u, and this velocity downstream is d. Let us say that this downstream velocity is d, and this is called as a branch takeoff. In such a scenario, you can calculate the pressure loss because of this branch takeoff as a function of, again, the velocity head rho v square, but this is now the downstream velocity, upon 2 into 0.4 into 1 minus the downstream velocity upon the upstream velocity square. Okay, so this sort of equation we can derive by using the Bernoulli's equation, and this is basically helping you to estimate the pressure drop in the branch takeoff. Okay, so by using such kind of expression, or as I said, if you are using the tables, you can straight away get the loss coefficient, and that loss coefficient into the velocity head will help you calculate what is the pressure drop in the branch takeoff. Just as you have a branch takeoff, there is something called as branch entry. Okay, so let me draw the branch entry also. So for a branch entry, similar to the place when we are talking about, suppose this is a main duct, okay, and you need to supply, let us say there is a return air coming into this main duct. So this is called as the branch entry. Again, you can use this. This is the angle beta. This is the upstream velocity u, and this is the downstream velocity d. Okay, downstream is d. Okay, and one can calculate upstream is u, downstream is d. So corresponding velocity is vu, and downstream velocity is vd. Okay, and let us say this is your some point here. You need to calculate the pressure drop in the branch entry. So how do we calculate that? Again, there is a relation in terms of velocity factor, rho v square d upon 2. This is the usual velocity head into 1.5 AD upon AB square. This is B, this area, okay, square minus 1. So this would help you calculate, the pressure drop in the branch entry. Okay, it can also be expressed in terms of velocity if you like. So the velocity expression, if you want, I can write down. It would be somewhat like this, that is Vd square rho by 2 again into 1 minus Vu upon Vd bracket square. Okay, so all in all, you have seen that what we have discussed is, just to summarize whatever we have discussed, we have discussed very important aspects. That is, we have discussed how to calculate the pressure drop in the fittings, and you'll always find that this pressure drop in the fittings is expressed in the terms of loss coefficient into the velocity head. Okay, and these loss coefficients are already tabulated. These are tabulated by using, they are calculated and tabulated in the handbooks. Okay, and how do we calculate that? By the empirical equations, which are from the equations which were given to you in the theory portion. Okay, so by using the beautiful expressions which we discussed here, we can calculate the pressure drops. Okay, and these pressure drops finally help you calculate what is known as the fan total pressure. And what to do with the fan total pressure? Fan total pressure is useful in calculating the capacity of the fan. Okay, so this was a brief review of the theory of the pressure drop in the fittings, okay, and pressure drops in the ducts, which you can skip if you don't like. Even if you are comfortable with using the data book, okay, and if you don't know the theory behind all this, it is quite okay. I hope you have enjoyed this lecture. Okay, thank you very much.